So in example problem 6.9, we're studying an example based on an electrophoretic fiber making process. The diameter of the fiber D is related to the current flow I, and the following were measured during production. So let's see here, they have one vector I, that equals a set of data. Notice some of these points are repeated. Okay, believe that is in without mistake, and then they compare that to a set of diameter data. There. So that is the data input. The relationship between the current and diameter can be modeled with an equation in the form D equals A plus B square root of I. So let's go over to a writing page to look at this a bit better. So the equation they tell us can be modeled by D equals A plus B root I. So obviously that is nonlinear. You have one of the main input variables in nonlinear form. The equation is linear if you consider this whole quantity to be your variable. So we will have to do that operation to the input set of data. We'll also take that other input set D, directly map it. It doesn't require any operation. And then the coefficients A and B can be readily determined through a linear curve fitting process. So in this case, we would have, let's see here, what is the independent? The independent would be I. Dependent Y, just directly mapped to D. So let's perform those operations on our input data. Let's say that Y variable equals diameter, X variable equals square root of I. Whoops, not that I. My bad. Capital I. There we go. Square root of all the data. Individually looks to be... yeah, looks to be right. Yep. Okay. So now we have mapped that data into our set of other variables. We would go through the same process we've done in other examples, taking Sx equals the sum of all x's. Sy, sum of all y values, whoops, equal sign would help. Sxy equals sum of x dot times y. So again, the dot is for the per element operations. Sxxx equals sum of x dot times x. Element by element, same thing as squaring each element and then summing them all together. So those are all of the input values. In fact, from doing another recent example, I should be able to go in here and say A1. No, I always forget n. N equals length. Either one, they should be the same length. Length of x, n equals length y. Thank goodness they're the same. So now I can go back up here from previously punching this in, say A1. Now that is equation 614 from the textbook. Again, this should just be entered somewhere. Maybe at this point you have a script that does this automatically because so many linear curve fits have been happening. So A1 does appear to be more or less correct when we confirm. Yep. A naught would be the analog to that. Negative 6.1967. Yeah, so that already are the correct A1 and A naught values for the curve fit function. So if we were to, let's see here, plot the x and y data, we get something that looks, oh, well, I should actually display it as particular points. Get something that looks like that. Now if we were to, in the same plot, create the array X of dependent data, we could do an anonymous function, but maybe we can make this even a little bit simpler. Let's just do the direct calculation right in one place. So that should be the y function, so it'd be a naught plus a1 times x dot, well, it's a scalar, a1's a scalar, so that should work. Let's see. Okay, pulled it off. So that line in linear space is the mapping of all those different points into a trend line. What would be interesting is to plot this in nonlinear space, back in the original equation form of I and D, to see how well that nonlinear equation works. So let's go back and remap these coefficients right quick. So with y equals d, that's pretty easy. Back in the form, we can just directly map that back. A and b require no remapping, so d equals, let's see here, a would be the a naught, b is equal to a1, square root of I. So that would be relatively straightforward. So instead of doing a plot of x and y, let's do a plot of I as the independent, d as the dependent data points. We would plot, again, I suppose we should do this on a more continuous basis, which we could, but I have to define that. So I'll make a variable x plot. What are the ranges of diameters in the question, since that was the independent? So diameters range from 22 to 42. So let's do 22 steps of 1 to 42. Fix my notation here. There we go. So it made that array automatically for me. So now I can go back to modifying what we'd initially done. So the independent would be diameter, dependent would be current, other way around. So here we would have x plot as the x-axis, a naught plus a1 times square root of x plot. I think that will work out. Should be a nonlinear form. If it doesn't, we'll fix it. Are all my parentheses balanced? Sure, let's see. Didn't go quite far enough. Okay, so instead of, yeah, because I changed the independent dependent, seeing which one was the output, that'd be fine. So I need to remap that. X plot, instead of being 22 to 42, let's do a range from about 300 to 650. Let's do it in steps of, I don't know, 10. No problem having the computer do more work. Okay. Run that command again. Hopefully we'll do the full range. There we go. So that is what the curve, the nonlinear curve fit looks like now, mapped back into nonlinear space. So you can still see it. It goes right through, you would call that the weighted middle of all these other points. It's very interesting to see that we've used linear methods to put a curved line right through the middle of a point cloud. So very successful tactic of taking measured data and generating approximate fits to that set.